NEC Article 384 covers commercial and industrial buildings. The code does not state that commercial and industrial installations should be treated differently for feeder calculations. In both cases, the general procedure in example D3 should be followed. Example D3 provides a method for calculating the minimum size of a feeder based on the sum of the non-continuous loads plus 125% of the continuous loads. This method is used for both commercial and industrial installations. The discontinuity factor of 125% is applied to the continuous loads to account for the fact that these loads may not be operating at their full capacity at the same time. This factor is applicable to both commercial and industrial installations. The apparent difference in the solutions for example D3 in the NEC text may be due to an error in the example. The actual load used in the example is 600 amps, which is less than the minimum feeder size calculated using the general procedure in example D3. This suggests that the discontinuity factor was not applied correctly in this particular example. In general, the procedure in example D3 should be used to calculate the minimum size of a feeder for both commercial and industrial installations. The discontinuity factor of 125% should be applied to continuous loads in both cases. If there is a discrepancy in the way example D3 is solved in the NEC text, it should be treated as an error. To elaborate, let's delve deeper into feeder calculations according to the National Electrical Code, or NEC. Feeders are conductors that carry electricity from the service equipment, such as the main breaker panel, to a subpole or a branch circuit overcurrent device. Properly sizing feeders is crucial for electrical safety and performance. It ensures that the conductors can handle the expected load without overheating, causing voltage drop, or creating a fire hazard. The NEC provides specific guidelines for calculating feeder sizes, taking into account various factors such as the type of load, the continuous or non-continuous nature of the load, and any applicable demand factors. The primary NEC article governing feeder calculations is Article 220, which covers branch circuit, feeder, and service calculations. This article provides the general requirements and methodologies for determining the minimum size of feeders. In addition to Article 220, other NEC articles may apply depending on the specific type of load or installation. For example, Article 430 covers motor circuits, and Article 625 covers electric vehicle charging systems. Now let's discuss the general procedure for calculating feeder sizes, focusing on the aspects that apply to both commercial and industrial buildings. Firstly, you need to determine the total connected load. This involves adding up the ampacities of all the loads that will be connected to the feeder. For general lighting and receptacle circuits, you can use the volt-ampere per square foot values specified in NEC Table 220.12. For specific appliances or equipment, use the nameplate rating. Secondly, identify continuous and non-continuous loads. A continuous load is defined as a load that operates for 3 hours or more at a time. Non-continuous loads are those that operate for less than 3 hours. This distinction is important because the NEC requires that continuous loads be factored at 125% for feeder sizing. Thirdly, apply the 125% factor to continuous loads. This means multiplying the ampacity of each continuous load by 1.25. This factor accounts for the potential for the load to operate at its maximum current for extended periods, which can cause the conductor to overheat if not properly sized. Fourthly, calculate the total load. This is done by adding the sum of the non-continuous loads to the sum of the continuous loads after they have been factored by 125%. Fifthly, apply any applicable demand factors. Demand factors are multipliers that can be applied to the total load to account for the fact that not all loads will be operating at their maximum at the same time. The NEC provides demand factors for various types of occupancies and loads in tables 220.42 through 220.56. For example, table 220.42 provides demand factors for general lighting in various types of buildings. Demand factors are typically expressed as percentages, and they are applied to the portion of the load to which they apply. Sixthly, determine the minimum feeder ampacity. The minimum feeder ampacity is the total load after applying any applicable demand factors. This is the minimum current carrying capacity that the feeder conductors must have. Seventhly, select the appropriate conductor size. Once you have determined the minimum feeder ampacity, you can select the appropriate conductor size from NEC Table 310.16. This table provides the allowable ampacities for various types of conductors based on their size, insulation type, and installation conditions. It is important to choose a conductor size that has an ampacity equal to or greater than the minimum feeder ampacity. Eighthly, consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop on feeders should not exceed 3% for power, heating, and lighting loads, or 5% for feeders plus branch circuits. To calculate voltage drop, you can use the formulas provided in NEC Informative Annex C. If the calculated voltage drop exceeds the recommended limits, you may need to increase the size of the feeder conductors. Ninthly, select the appropriate overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The NEC requires that overcurrent protection devices be sized to protect the conductors they are intended to protect. The general rule is that the overcurrent protection device should have an ampacity equal to or less than the ampacity of the conductor. However, there are some exceptions to this rule, such as for motor circuits, where the overcurrent protection device may need to be sized higher to allow for motor starting current. Finally, ensure compliance with all applicable NEC requirements. Feeder calculations must comply with all applicable requirements of the NEC, including those related to conductor sizing, overcurrent protection, grounding, and installation methods. It is important to carefully review the NEC to ensure that your feeder calculations are accurate and compliant. Now, let's address the specific issue raised about the difference between example D3 and example D3 in the NEC. As noted earlier, the NEC does not state that commercial and industrial installations should be treated differently for feeder calculations. The general procedure outlined above should be followed for both types of installations. The discrepancy in example D3 may be due to an error in the example, where the 125% factor was not properly applied to the continuous loads. To further clarify, let's look at an example of how to calculate feeder size for a commercial building. Suppose we have a commercial building with the following loads: general lighting 20,000 volt amps, receptacles 10,000 volt amps, HVAC equipment 15,000 volt amps, and continuous lighting 5,000 volt amps. Firstly, determine the total connected load. The total connected load is 20,000 volt amps plus 10,000 volt amps plus 15,000 volt amps plus 5,000 volt amps, which equals 50,000 volt amps. Secondly, identify continuous and non-continuous loads. The continuous lighting is a continuous load, while the general lighting, receptacles, and HVAC equipment are non-continuous loads. Thirdly, apply the 125% factor to continuous loads. The continuous lighting load of 5,000 volt amps is multiplied by 1.25, which equals 6,250 volt amps. Fourthly, calculate the total load. The total load is the sum of the non-continuous loads 20,000 volt amps plus 10,000 volt amps plus 15,000 volt amps, which equals 45,000 volt amps, plus the continuous load after factoring 6,250 volt amps. This sums to a total of 51,250 volt amps. Fifthly, apply any applicable demand factors. Let's assume that we can apply a demand factor of 80% to the general lighting load, according to NEC Table 220.42. This means that we can reduce the general lighting load from 20,000 volt amps to 20,000 volt amps multiplied by 0.80, which equals 16,000 volt amps. The new total load is 16,000 volt amps plus 10,000 volt amps plus 15,000 volt amps plus 6,250 volt amps, which equals 47,250 volt amps. Sixthly, determine the minimum feeder ampacity. Assuming a 208-volt three-phase system, the minimum feeder ampacity is 47,250 volts divided by 208 volts multiplied by the square root of 3. This equals approximately 131.2 amps. Seventhly, select the appropriate conductor size. According to NEC Table 310.16, a 1/0 AWG copper conductor with THHN insulation has an ampacity of 150 amps, which is greater than the minimum feeder ampacity of 131.2 amps. Therefore, we can use 1/0 AWG copper conductors for the feeder. Eighthly, consider voltage drop. We need to calculate the voltage drop on the feeder to ensure that it is within the recommended limits. Using the voltage drop formula in NEC Informative Annex C, we can calculate the voltage drop based on the conductor size, length, and current. If the calculated voltage drop exceeds 3%, we may need to increase the conductor size. Ninthly, select the appropriate overcurrent protection. The overcurrent protection device should have an ampacity equal to or less than the ampacity of the conductor. In this case, we can use a 150 amp circuit breaker to protect the 1/0 AWG copper conductors. Finally, ensure compliance with all applicable NEC requirements. We need to ensure that our feeder calculations comply with all applicable requirements of the NEC, including those related to grounding, bonding, and installation methods. Now, let's consider a similar example for an industrial building. Suppose we have an industrial building with the following loads: motors 50 horsepower, welding machines 30 kilovolt amps, and process equipment 25 kilovolt amps. Firstly, determine the total connected load. The total connected load needs to be calculated based on the nameplate ratings of the equipment. We need to convert the motor horsepower to kilovolt amps using the appropriate conversion factor. Assuming a typical power factor of 0.8, the motor load is approximately 50 horsepower multiplied by 0.746 kilowatts per horsepower divided by 0.8 power factor, which equals approximately 46.6 kilovolt amps. The total connected load is 46.6 kilovolt amps plus 30 kilovolt amps plus 25 kilovolt amps, which equals 101.6 kilovolt amps. Secondly, identify continuous and non-continuous loads. We need to determine which loads are continuous and which are non-continuous based on their operating characteristics. Let's assume that the motors and process equipment are continuous loads, while the welding machines are non-continuous loads. Thirdly, apply the 125% factor to continuous loads. The continuous loads motors and process equipment are 46.6 kilovolt amps plus 25 kilovolt amps, which equals 71.6 kilovolt amps. This is multiplied by 1.25, which equals 89.5 kilovolt amps. Fourthly, calculate the total load. The total load is the sum of the non-continuous loads 30 kilovolt amps plus the continuous loads after factoring 89.5 kilovolt amps. This equals 119.5 kilovolt amps. Fifthly, apply any applicable demand factors. Depending on the specific type of industrial occupancy and the nature of the loads, we may be able to apply demand factors to reduce the calculated load. For example, NEC Table 220.48 provides demand factors for non-coincident loads in industrial occupancies. Let's assume that we can apply a demand factor of 75% to the welding machine load. This means that we can reduce the welding machine load from 30 kilovolt amps to 30 kilovolt amps multiplied by 0.75, which equals 22.5 kilovolt amps. The new total load is 89.5 kilovolt amps plus 22.5 kilovolt amps, which equals 112 kilovolt amps. Sixthly, determine the minimum feeder ampacity. Assuming a 480 volt three-phase system, the minimum feeder ampacity is 112,000 volt amps divided by 480 volts multiplied by the square root of 3. This equals approximately 134.7 amps. Seventhly, select the appropriate conductor size. According to NEC Table 310.16, a 1/0 AWG copper conductor with THHN insulation has an ampacity of 150 amps, which is greater than the minimum feeder ampacity of 134.7 amps. Therefore, we can use 1/0 AWG copper conductors for the feeder. Eighthly, consider voltage drop. We need to calculate the voltage drop on the feeder to ensure that it is within the recommended limits. If the calculated voltage drop exceeds 3%, we may need to increase the conductor size. Ninthly, select the appropriate overcurrent protection. We can use a 150 amp circuit breaker to protect the 1/0 AWG copper conductors. Finally, ensure compliance with all applicable NEC requirements. We need to ensure that our feeder calculations comply with all applicable requirements of the NEC, including those related to grounding, bonding, and installation method. In both the commercial and industrial examples, the same general procedure for feeder calculations was followed. The 125% factor was applied to continuous loads, and demand factors were applied where applicable. The key is to carefully identify the loads, determine their characteristics, and apply the appropriate factors and calculations according to the NEC. It is important to note that these examples are simplified for illustrative purposes. Actual feeder calculations can be more complex depending on the specific loads and installation conditions. It is always recommended to consult with a qualified electrical engineer or contractor to ensure that feeder calculations are accurate and compliant with all applicable codes and standards. In summary, feeder calculations for commercial and industrial buildings should follow the same general procedure outlined in the NEC. The 125% factor should be applied to continuous loads, and demand factors should be applied where applicable. Any discrepancies in NEC examples should be treated as potential errors and carefully reviewed.